Thank you very much for the kind introduction. I'm talking about geospatial analysis, and the second thing you see, the title is JupyterHub. Any one of you already used JupyterHub before? Oh, cool. So not too many, but more and more and more. That's great. Actually, I could have titled the talk with Jupyter Lab instead of JupyterHub, but I want to show you how cool JupyterHub is. It's basically Jupyter Lab where you can log in. So if you go on a website and you have a JupyterHub installed, you just get this page here and you can sign in. And after signing in, you see this. So it's perfect. So it's a multi-user Jupyter Lab, and that's pretty much all. There is something I like to show you too. This one you can do with a regular Jupyter Notebook or Jupyter Lab installation too. You see I have 3 kernels here. I have a Python kernel, I have a Markdown kernel, I have an R kernel. But there is another feature, you can have kernels with different Python versions, and that's quite handy. And you just create a virtual environment. You see that above, using Conda in our case. And environment name, whatever you like, and then you specify Python 3.5, 3.6, 3.7, whatever, don't use 2, and the IPython kernel. And then you activate this environment and install all your cool packages you want to use, and after that you can create a new kernel with the line above, just IPy kernel, install, user space, and name of the new kernel. And the screen turns black. And then you can list all the kernels using Jupyter kernels backlist, and you see actually all the kernels installed. So if you make this procedure for, let me say, 5 different Python versions, you will see actually 5 different Python versions in your Jupyter Lab environment. And that's really quite handy. And now we come back to the original title, Geospatial. If you install geospatial modules, then you usually have to install many C-based libraries. And for that, it's really, really recommended to have multiple Python versions and environment. And of course, if you are on JupyterHub, you will have your file system there, and you can access all your user files from the Jupyter Lab or Hub. So what we are doing, we have a HBA Apollo 6500 server, and on this server we installed JupyterHub, and we bought this machine with 48 cores, 192 gigs of RAM, and attached it to our small storage system with 120 terabytes. Which is actually quite fast storage, where we have 1 GB per second reading and writing speed. And that's also a very important fact. If you have terabytes of geodata, you want to have a really fast and reliable system. We also have 4 NVidia Tesla V100 in it. Wow, that's high-tech here. So I think the cable should be changed tomorrow. Okay, so what I wanted to say, we have NVIDIA Tesla V100, the SXM2 model. That's here, one of them, and uses lots of power and has 900 GB bandwidth, so it's quite fast. That we use to create our deep learning models. More about that maybe later. So what is geodata? There are some standards, ISO standards describing what's geodata, the Technical Commission 211 series, and so on. But the most important is most data you have has a geospatial component. Most data you actually have has a location component, or you can create a location component out of it. And mostly people use GIS software to load and manage this data. However, that's something I do not want to do personally. I use Python for that. So what I show you now is everything I'm doing with GeoData is done in a Jupyter Notebook, and you can really uninstall all JS software if you do that. And today I'm limiting myself to vector data and a little bit raster data. There is also other geospatial data like point clouds and 3D objects, and that's not what I'm going to tell you. So everything is open source I'm showing today. The most important two libraries are C++ based. It's GDAL OGR. Okay. And the second library is Geos. And they have bindings in Python, and it's really, it's not Pythonic. So therefore, some people created new Python modules which are really Pythonic and use the same C++ library, and it's much, much nicer to work with that. I would not recommend using GDAL directly. I would use Rasteria for raster data processing, Fiona for vector processing, and Shapely to do some vector data operations. I will show you in an instant. And if you know pandas, really nice module in Python, there is also GeoPandas, which extends pandas for geospatial data. So that's, I give you the links, which projects we are looking at today. The most important is that we use Jupyter Notebook, and the first module I'm showing you is Folium. Folium is basically Leaflet.js JavaScript library to create maps. It's one of many JavaScript libraries to create maps, and with 3 lines of code you have a map in your Jupyter Notebook or Jupyter Lab. So you can specify import a Folium module, and you just create a map. You specify a location and a zoom level. The zoom level is how far you are away from the ground. There are typically about 20 zoom levels. You know that from other mapping services like Google Maps, Bing Maps, OpenStreetMap, Yahoo Maps, and all these map services that exist today. Another thing is, if you look at vector data, there are some specifications like the OGC simple feature access specifications, where geodata and in this case vector data is defined. This is used in many databases like PostGIS, PostgreSQL, and so on. And one of many representations is just using text. So I use text to specify a point. I use text to specify a polygon, and so on. The reason for that is you can print it, and in 100 years you can still read it. So in the Geo world, that's a very important topic. There's also the WKB, a binary format, but I'm not talking about that now. So here are some examples. If you specify a point in WKT, well-known text, it's just point, brackets 10, 20 in this example. Or if you have polygon, it would be polygon, text for the coordinates. Or there are some things like multi-polygons. So you have multiple polygons. For example, if you have a country with islands, there are multiple polygons in that. There are also countries with holes, and then you have a hole. This is all specified in a WKT, so it's a nice thing. And we can use that directly with Shapely. We can use that directly. So we can create something similar like the WKT, just using a Python list and tuples for the coordinates. And you see you create, you import polygon, import point, and here you just specify your polygon. And if you look at it, you see the first and the last point is the same. That's an important aspect of this standard. The first and the last point is the same, so we have a closed polygon. We can actually load it from text too. We can create a string with the WKT definition and load this using Shapely WKT and just load S for string, and then we have our polygon definition. Another format which is quite popular in the JavaScript world is GeoJson. And there you also create your polygons and specify the coordinates. That's another approach to define vector data. Of course, there are many other formats too. I'm not going into details there now, but that's what you find if you go into the geo business. So let's just add such a GeoJson in volume. You see, it's a little bit more complicated, but basically you open the GeoJson file, you load it, and you put it on the map. Again, same syntax, and then you use the GeoJson from volume, it's just called GeoJson, and you add it to your map. In this case, I loaded a GeoJson of Switzerland. Okay, you see that, it's the shape of Switzerland. And now I do the same again, but I plot it directly using Shapely, and you see there is it's not the same, so there is a distortion. So Switzerland is not that distorted usually. And the reason for that is we have different coordinate systems. So yeah, let me show you the graticule on a sphere. You know that there is longitude, latitude. Longitude along the equator, latitude for the poles, and you can project this to a map. The easiest way is just to create out of the sphere, you just create a Cartesian coordinate system. So you do map the latitude, longitude on it, and then you get this one, and that's a completely distorted image of the world. It's not what you see in Google Maps, actually. There is even more bad with more distortions. So there are some definitions. The Earth is an ellipsoid, so the World Geodetic System 1984 defined some data how the Earth is best fit in a rotational ellipsoid or spheroid. And out of that, you can create different map projections. I took 3 here out of many 10,000 different. Actually, you could invent your own map projection if you want to. And here I printed 3 of them. And you see they are all a little bit different. The Mercator projection is what you know from Google Maps, etc. And you see the Antarctic down here is bigger than most other continents, which is completely wrong, but it's an effect of projections. So we can look at these so-called coordinate reference systems or spatial reference systems, and we can have 2 special cases. One is we use geocentric Cartesian system, that's just a Cartesian system with x, y, z. Or we use projected coordinates. That's usually not 3D, it's actually flat. And that's, actually every country has its own representation. Switzerland has its Swiss grid, and for example, also countries that have their special coordinate systems too. I'm not going into details here, but you can look it up at epsg.io. You can look the system of your country. EPSG is the European Petroleum Survey Group. They catalog all these coordinate systems. And for example, the EPSG 4326 is the World Geodetic System 1984. Okay, that was a little bit off topic. Let's look at the real example. We are located around here. So we can say we have a longitude of 7.5. So here, Greenwich is 0, and we are 7 degrees to the east, and then 47 is the latitude. So here would be the equator, so we go 47 up. Oh, it's here, yeah, and we are in Switzerland at the Congress Center Basel. So that's how it works. Maybe the problem we will see in an instant. So with Shapely, we can do some nice expressions. We can check if a point is inside a polygon, for example. That's a very complex operation, but with Shapely, it's just a few lines of code, actually 1 line of code. So you create a point, 47.7, that's our coordinate of the Congress Center Basel. I can look at it as WKT representation. I see point and the coordinates, so everything is perfect. And then I check the operation. This EuroPython point is within Switzerland, and we get the result false. So what did I do wrong? Lowercase, wrong projections, all wrong. So no, it's very simple. It's very simple. You see, I show you the result how it is done correctly. So what was the difference? I flipped the latitude, longitude. Now I have the longitude first, and then it works. So the problem is, before we had the volume module. Volume says first latitude, then longitude. Shapely says first longitude, then latitude. And that's a that's a common problem. Some people say lat long, lat long. This is better. No, that is better. And the confusion is perfect. So we have to always consider that and know which module uses which representation. Personally, I prefer this approach too, because it's something like x-axis first and y-axis second. But in geographic coordinates, you can't say x-axis and y-axis. So that's the point of where many people find it's worth disputing. So I said before, we have other vector formats. I'm not going into the details. I just recommend if you want to read vector data, use the Fiona module. But as the time is going on, I'm showing quickly GeoPandas, which is pandas with the ability to make some geographic or geospatial queries. So I can load something. Let me load a data set with all cities of the world with more than 5,000, with a population greater than 5,000. You can download this data set at geonames.org. So it's very small, so you don't see that well, because it has many data in it. So I reduced it to the most important data. So I take the name, latitude, longitude, population. Now you see I take latitude first and longitude. And that's the data set. You can create a GeoPandas out of it. The trick is you make a column with named geometry. And in this geometry, you have a shapely representation of the geographic information. This could be a point, like in this case, or a polygon, a multi-polygon, or whatever. You can create your geometry column just there. So GeoPandas can also plot, like we know that from pandas. Just make your geodata frame and you plot it. And if you plot all cities of the world, you see, you recognize the shape of the continents, more or less. Europe is quite green in this case, so there are many cities. So I can do some queries. It's basically pandas, so it's the same. And you see if I make query, name Basel, I get Basel information. But more interesting are spatial queries. So let me get the distance from the Congress Center here to all other cities in this data set. So I just create our point again and calculate the distance and make a new column with distance, and I sort this column distance. So I show you the result. It's simpler to understand. So you have the name here and the geometry and here the distance. So you see we have Birsfelden is just next to Basel and Basel itself. So it's a little bit strange because it's always the center. So it's the distance to the coordinate. So we are closer to Birsfelden than to Basel. Binningen, Weil am Rhein, that's in Germany. Saint-Louis, France, and so on. So that's the names of these areas with the distance. So I can also query within a polygon. So I can use my polygon again and say I would like to have all the cities within the polygon Switzerland. And then we see if I do that and combine it with something else, like, for example, I would like to have all the cities with a population bigger than then 20,000. And I return, this is not sorted actually, but it doesn't matter. So I get all the cities in this data set within Switzerland and with a population greater than 20,000. So let's do one more thing, display the cities in a volume map. That's quite easy. You can combine those modules. So you just create, with apply, for example, you can specify a function which creates marker of every city, and then you have that in volume. So let me do a last example before the session chair throws me out. There is, for example, a nice data set with live earthquakes, or the earthquakes of the last 2 weeks. So you can download that directly with this link. I do that, for example, with the requests module, and then I store it as a file, earthquakes, GeoJson. I just did it half an hour ago about, and that was the result. So I can use GeoPandas to open my GeoJson directly and display the first 5 incidents. And again, I simplify the dataset. I reduce it to 4 columns: time, magnitude, place, and geometry. We see the first 5. It's not sorted anyway. And yeah, we see a trend in California at the moment. There is a hotspot there at the moment. And we can create a histogram out of the data. That's a nice way. Using histograms with 16 bins in this case, we see luckily most earthquakes are so around 3, and there are higher ones in there, unfortunately. And we can, you see in the first column here, you have a timestamp, and to change this timestamp to a better readable representation, you can use the datetime and the time zone module of Python and create a new column which is more readable. So we have 10 of July. This is UTC time zone. Maybe we hear something about time zones in a lightning talk. I don't know. Oh, tomorrow. Okay. A very nice talk about time zones, very important. Miroslav. So we can plot this, and we can also plot multiple geodata sets. And you see, I read this geodata frame, and I can combine this using just plots, multiple plots, using the axis. You can have multiple plots, so I can display the continents and some earthquake on it. You could do more. You could change the size of the dots depending the magnitude. And I think the cable says it's time for questions. So thank you very much for your attention. And are there any?
We have plenty of time for the questions. We have 5 minutes, so please. I'm struggling with mics. They don't look like they are. They're not professional.
Yeah, I think that's. Actually, there is a microphone on the table, I think, somewhere. I'm not quite sure.
Hello?
I'm not sure.
Can you say something about what you use this very expensive computer for?
Yeah, that's a good question. I unfortunately wanted to say more about that, but I was running out of time. After 35 slides, I said, oh, I have to stop slowly. We do some project, for example, to detect solar panels on the roofs. We have the data set of orthophotos of whole Switzerland. That's about 2 terabytes of data. And there we try to detect solar panels, different kind of solar panels. And therefore, we create models, deep learning models, and train that. And for training, we use the 4 GPUs and to improve it. Oh, there. It's confusing with the microphone. Okay. And of course, many other applications. We do many deep learning projects at the moment.
If we don't have questions, you can maybe show a bit about this, about
No, I didn't skip. I actually didn't even put inside in this presentation.
I mean that we have 5 minutes.
Yeah, but I don't have it ready actually to. Okay.
Are there any solutions for geodata spatial queries in databases in Django applications you would recommend? Because we've seen Python now, but if I have to trim it down to SQL, it becomes a bit more complex, especially when I have to do it from a Django direction.
Yeah, of course you can. This is something I don't like to answer in a Python conference, but you ask me now. So, for example, there's PostgreSQL and PostJS. And PostJS uses spatial queries too. You can do the same like I showed here. And unfortunately, you can do that with PostJS much faster than using the Jupyter Lab solution I showed you. So what I showed you is actually slower than if you are using Postgres. So, but you can do actually the same. The disadvantage, of course, is you don't have a nice Python environment. You can't program it nicely like this. You can just do queries.
I'm aware of that, but it's a feature of a specific database, and if I want to do it from Django, yeah. and the Django query should also work with SQLite, then I think I can't just use the Postgres
Are you aware
features.
of the project GeoDjango? There is a GeoDjango which takes care of these details, so you can directly access the features of PostGIS with GeoDjango.
Some possibilities to use these libraries for the planets other than Earth, so Mars or.
Yes, it's actually no problem. You can do any planet. The only problem is that you don't have high resolution data of other planets, but it's basically the same. You just need the model. There are models for Mars, for example. There are models for most near planets. On Earth, we have the WGS 84 representation, but the Mars is basically also an ellipsoid, so you can do exactly the same calculations. You could even do distance calculations from one point to the other with GeoPandas and a Mars dataset, so it's no problem.
Okay, thanks.
Yes, I will make them. I think all EuroPython slides will be on the program, on the website program. So all speakers will upload them, and you can just download it from the place where the schedule is. So it's just click on the topic, and you will get the link to the slides.
Could you maybe shortly talk about the limits of these libraries, where you end up with like with geodata, you often have like very large scale information. When you load them in a Jupyter Notebook, it could get interesting.
That's a very good question. Don't use GeoPandas for very large data sets. It's same like pandas. You can't use pandas for very large data sets at the moment. The developers are working on that. They try to do some memory voodoo. Sorry for that. But it will not work unless you use modules. I didn't show that because it's already too much in the detail. If you use Fiona, for example, you can take one row of the data set, and you have that in the memory. So you have to do the memory management yourself. For example, if you want to do some distance calculations, you would just do it on a per row base. And then you could take a multi-terabyte data set and do your calculations with that. There is also, for larger data sets, there is PySpark and GeoPySpark. See, there is a trend in putting a geo in front of classic Python modules. And with GeoPySpark or PySpark, you can do much bigger calculations.
How many points, how much gigabyte can you load at once?
Actually, there is almost no limit. It's a hardware issue. If you have enough money for the hardware, you can have unlimited amounts of data. Okay, thank you very much again.